A common problem with cheese graters is that users are always exposing their fingers to the blades as the cheese gets smaller, risking getting cut as they continuously swipe against the blade. One solution is having a 4-bar crank slider mechanism, which moves the cutting blade in a cyclical linear motion and keeps the user's hands safely away from any sharp edges. Motion is caused by turning the handle on a wheel at a fixed point located on one end of the mechanism.
The kinematic goal for the mechanism is to decrease the time it takes to grate cheese compared to a typical hand grater. The relationship between the angular velocity of the crank and the linear speed of the grater is very important, as is the length of the coupler. Experimental data was collected by simulating the motion of the mechanism. This data led to our assumptions of 2 revolutions per second for the crank and 21.6 centimeters per second for the handheld grater. This table shows a relationship between the length of the coupler B and the linear velocity of the grater d dot average. We chose a 20 centimeter coupler because it was the best balance between linear velocity and being long enough to reach the end of the grater. These equations were used to calculate all the non-free choice variables for the mechanism. This plot shows the variation in linear velocity as the crank makes a full revolution based on the chosen 20 centimeter coupler. The table shows the data that generated the plot, including assumptions for the different link lengths and angular velocities.
With dynamic force analysis, our main concern is how much input force is needed to turn the crank at the handle. After taking the information provided by the results from our kinematic analysis, that is, the positions, velocities, and accelerations, as well as masses and mass moments of inertia of each component in the system, a matrix equation is compiled to solve all unknown values in the system. To simplify calculations, it is assumed that all links are rigid and joints and pins are frictionless. After finding the applied force, we compared it to the force done by hand on a simple grater. Comparisons showed our design requires the use of less force to turn the handle of the crank versus applying pressure to the cheese directly onto the blade as it grates. Therefore, the crank slider design is at least 3% more efficient to use for this purpose.
For our stress calculation, we assumed that the coupler and the 2 bolts attached to it would be under the most stress. Therefore, we calculated the buckling of the coupler and the bearing stress for the 2 bolts attached to it. Knowing that we had a long, slender coupler, we knew that buckling would be a major factor in our calculations. In the end, we used Euler's equation to calculate for the stress at which buckling would occur. However, we were surprised when we found that the stress was well in the 900 range, and our stress was at 23.2 on the actual coupler. This resulted in a huge safety factor well in the 200s for our device. For the bolts, we used the bearing stress equation and calculated both safety factors to be over 3, which corresponded with our desired safety factor of at least 2. Although we used wood for all of our calculations, our safety factors were very high, which means that our original desire to make it out of aluminum would be more than safe for household use. Looking at the device as a whole, we see how useful it would be in daily life, and not only how useful, but how safe it would be. So safe, in fact, that perhaps if a young kid would like to help his mother or father out in the kitchen, they could with relatively little effort, and little chance of them ever getting hurt by the device.